question, so I just want to remind you what we were doing last time. I'm not going to put up the graph, but remember that reversible work is the most negative or the least. Both of those mean the same thing. And although I don't like that term, obviously we like to say the most negative, so it's still a big number just with the minus sign. But if you're doing a compression, then it would be the least positive. So that's a little funky. Now, again, I'm not going to repeat last lecture, but whatever work does, heat will do the opposite. And so I write this. Now remember, we can do this with graphs. This is absolutely true. And I'm just pointing out that what work does, heat will do the opposite. And I'm using an isothermal type of example, but that's fine. I can really use any example. I can use any example because when I divide by T, now I'm talking about the state function entropy, and that is path independent. So, excuse me, I've set this up with a path in mind, but the fact that I'm ultimately describing something that's path independent, this is totally fine and correct. And of course, then you recognize this as entropy. And this by itself is like la-di-da, so what? And in all honesty, it really does seem like that, except that you recognize that actually, if I state that the outside entropy only changes with the heat transaction, then this is actually the second law of thermodynamics, because this becomes the change in total entropy. All right. Now let me, again, I'm just going to briefly go through everything I did last time. If we then multiply by minus, I'm going to do this slightly differently, by the way, just for the heck of it. Okay, so I'm just multiplying by minus t because I felt like it, or that's what it seems like. I've got this. And the only hard part is, and I generally do have you do something like this on the test, the only hard part to remember is that if 5 is greater than 0, that minus 5 is less than 0, right? 5 is greater than 0, minus 5 is less than 0, because t's are always positive. That's why I'm always talking about it. It's positive versus negative. And then I can make stipulation at constant volume, then heat would be internal energy. And I've got this, and then I can say at constant entropy, the change in U is less than or equal to 0, which is actually exactly the same thing as in freshman in high school, hopefully in high school. We always told you that delta G being negative meant spontaneous. Now remember, a few days ago I said total entropy increasing is spontaneous. I redefined that. It probably just kind of slipped over your head. And then I said, no, it's delta G, because delta G is actually total entropy. And now I'm saying it's change in U is total entropy. I keep reversing myself. That's to ease you into this whole process. So a negative delta U, not delta G, a negative delta U stipulates whether a process is spontaneous, but it has to be a constant V and constant S. Right? Now that actually, there is a way to do that. How do I hold volume constant? Okay, that's brainless. You put your chemical process in a stainless steel like cell. We call those bombs, by the way, for some reason, because they can be. All right, but anyway, it's not hard to do a chemical reaction in a closed vessel. Constant S, how could I do constant S?
You can't.
Oh, yes, you could. 80-beta reversible, right? All the entropy changes are 0. Right, so a chemical process in a closed cell that's 80-beta and reversible. If you want to know whether that change is spontaneous, then don't forget delta G. That's pointless. It's delta U. And actually, if you look around, you might be able to find tables of delta U's, like you can find tables of delta G. I'm actually not sure about that. Anyway, now also at constant, I was kind of blowing through this because I ran out of time. Mind you, at constant P, that H is heat, and then of course we still have to stipulate at constant S that the change in H is less than or equal to 0. Is again the definition of is it spontaneous? The definition of does total entropy increase? So we have again the big picture of total entropy always increases. That's the second law of thermodynamics. But because we practically analyze any chemical process, biological process, you can't be a constant pressure and constant volume at the same time. You've got to find a way that there's descriptors for how things happen. Again, you can't simultaneously do things at constant pressure and constant volume. So when you're analyzing something, you have to figure out how it's being done, and then that allows you to whittle away at what's important and what's not via what I just did, by the way. Again, figuring out what's spontaneous. Another important thing about this, so why bother? Because I don't have an entropy meter, right? If I had an entropy meter, then none of this, I could still do this, but it just wouldn't matter. I just use the entropy meter. I don't have an entropy meter. I do have an energy meter. Right now, I know change in U is a little bit foreign to you, but you know change in H. You've been doing change in H since high school, right? That's entropy. That's heat in, heat out. And so you know that you can measure this. Again, you did this when you made those little styrofoam cup calorimeters. You'll do it in PChem lab too. It's kind of embarrassing, but we actually had to do a quick calorimetry experiment to keep you busy at the beginning when we're actually still making sure the labs actually function. So anyway, my point is, you know enthalpy, you have measured enthalpy before. This is a very real thing. Entropy, you cannot really do that. And so this is why this stuff is actually important. It tells you whether something is spontaneous or not. Okay, now this is as far as I can get with this, but now notice that again, I have been stipulating that these require constant entropy, and great, for adiabatic reversible, yeah. That is not actually useful. Most processes are not adiabatic or reversible. Besides, that would be an equilibrium process, right? Reversible automatically means equilibrium, and I don't really study things at equilibrium because that's kind of the same thing. You know, things that happen at equilibrium. I'm going to go over that more in about a month, but so don't worry about it right now. But for the most part, equilibrium things are standing still. Your car, when moving down the street, is not at equilibrium. It is when it's not moving, but I don't care. Okay, so, and you already know that I should be talking about delta G at some point, so where's delta Y is delta G minus, and I hinted at this last time, but I want you to recall, remember this thing? Legendre transforms, right? So hopefully you've already figured out that G is H minus TS, sounds a lot like H is U plus PV. Those are all Legendre transforms. Let me remind you, and then of course I'm going to define G by a Legendre transform. Hopefully that's obvious. And walk you through it. Now I've already done all this, so I'm going to say the change in U is the change in work. I'm going to write this reversibly because I can, because I'm talking about something that's a state variable. If I don't do it reversibly, I can get the answers that I'm going to get. Just going to take 10 more steps as opposed to 1. And you know I'm going to be doing heat, which by the way is going to be TDS in a minute, but for now let's just remind ourselves how this works. When we talk about the change in a function, is the change in a function with respect to a variable is something else held constant. That thing constant, by the way, is entropy. I know I didn't tell you that last time. So then, of course, let's let's define terms. F is, of course, mu. X is, of course, v. And more importantly, df times x at constant y is minus p. Right? Okay, and so what I can say from that is, therefore, the conjugate of v is minus p. Now, by definition, remember that this function has x as a natural variable, and so u is a natural function of the variable v, not p, but v. And the conjugate of v is the thing that it's multiplied by. In that case, it's minus p. Those are just definitions, all right? So there you go. And from this, remember that the Legendre transform, so you might want to write that down, is the original function minus the thing that you're kind of sick of. Again, we're going to, sorry, we got rid of volume before, but you have to multiply that by the conjugate of that variable. And G is now a function of no longer the variable x, it's now a function of the conjugate of the variable. Again, back into our previous language. Well, here, let me do it by example. That's a little bit easier. I didn't like U's dependence on V, so I subtracted it out times the conjugate. And so that's H plus PV. Again, you've seen this before. Hopefully you're not even writing it down. And there you go. All right, so tell you what, let me grab a new board. So what I'm going to start doing is defining new functions. All right, I've beaten volume to death. There's nowhere else to go with that. I have subtracted the volume dependence on U. I've placed it on H. Don't forget that the way you figure out that H has a natural variable that's not volume but pressure is you look at the change in H. When we did that last time, we'll do it again just in case you forgot. Okay, anyway, so I've beaten volume to death. Let's now do entropy. Okay, so let me write out the whole thing for U. Okay, now again, a little side derivation. The change in reversible heat over temperature is the change in S. Okay, now remember that this is reversible work. I choose to do reversible work, but if I've added the reversible work, I need to add in the reversible heat. You're kind of obliged to do that. Not a big deal. But instead of adding in heat, I'm going to add in TDS. Right? Just, yeah, it's shockingly easy. Right, so now I have built the entire change in U, which mostly gives me an unbelievably large number of ways of doing derivations. Question?
Up there, it says H equals H plus PV.
Yeah, because the conjugate is negative. Remember, you subtract the thing you don't want times its conjugate. We subtracted B, the conjugate was minus B. You've got to pay attention to those minus signs. They are crucial. So minus, minus, plus.
You mean U instead of H?
Wait, U plus PV. Right. Sorry, I thought you were complaining about my bad. That's going to take me a long time to fix on that. Freaking, yeah, U plus PV. H can't be equal to H plus PV. Sorry about that. Guys, stop me sooner, right? That's going to cost me so much time on that editing software. Someone please tell me, what can I use other than Microsoft Movie? That thing takes hours.
You could also just like do an annotation on YouTube over that and like place it in.
Okay, well that might save me some time, but I'd rather fix the video directly because I do save them.
Yeah.
Just in case, yeah. I think Adobe has something, right?
Just put it down and fix it.
Okay, there you go. My problem. I'll fix it. All right. So now remember that this means that U is a function of B and S, right? Remember when I said when you're trying to figure out what the natural variables are, you just look at you look at how it changes and what makes it change. I'm looking at the change in U, and what makes it change are V and S, and so U is a use natural variables are V and S. Okay, so now what I want to do is, and I won't screw this up this time, I want to get rid of the S dependence on U. And again, that's because S is a Bisnocker. I don't have any good way of holding it constant. And if I can't hold S constant, then total entropy increasing means that change in U is negative or change in H is negative is kind of not useful. Okay, but if I had a different energy function that wasn't dependent on S, but on T, which I can control, that would be much better. Okay, so I'll subtract S, and what's the conjugate? What's the thing that multiplies S? It's all right, it's T. Right, so we traditionally say TS, so I kind of was about to write it backwards. Anyway, yes. The thing you don't want, the thing that's problematic times the conjugate. Now remember, I just defined conjugate a zillion times up there. And this is A. This is called A, it's not G. We're not at G yet. A is something you probably have not seen before. This is called a Helmholtz Energy. A becomes from a German Arbeit, I believe. Which any of you German speakers, am I saying that right?
Means work.
Well, it means work. So, and it does bring up one other thing. I do try to be helpful to folks, and if you ever do get stressed out, especially when you get your test back, seriously, just take it easy, close your eyes, and count from 1 to 10. screaming in German. It will get that tension out one way or the other. A is called work, the work energy for a reason I'll explain in a moment. What I want to do is figure out what its natural variables are. It better be V and T, right? That's why V's dependence is preserved in U, but I've taken away U's S dependence and put it on T. That's the idea. The way you verify it, again, is by looking at the change. And so that's the change in U minus the change in TS. Okay, and I've got this person memorized. That's my PDD plus TDS. Okay, and now again, remember I've said many times, you got to make sure you know how to do with these product rules, right? Minus TDS minus STP, right? You just unmute. Okay? Okay, so this is minus PDD minus SDT, and therefore A is a function of V and T, which is now infinitely more useful than U was, because I can see already that, and you're going to do this on the homework, so I'm not going to do this now. I'm going to do a hard problem class, by the way. If you do that whole Clausius inequality deal, and you do it with you do it with constant volume, which allows you to replace the heat, the change in heat with the change in U, and then you stipulate that the temperature is constant, you'll find that a negative change in A, again, constant volume, constant temperature, is associated with spontaneity, is associated with a net positive change in total entropy. Again, that's the definition of spontaneous. Let's see, there's, so I'm going to have you do that on your homework. Instead, I'm going to do the hard one, which is G. But before I get to G, I have to go through H to get to G. So let me remind you about H, and I won't screw this up. What's the change in PV? And therefore, this is PDS. I'm switching the order because I've got this term PDV plus PDV plus VDP. Now again, you can see this would be a mid-level question on the next exam. And I see that enthalpy is a function of entropy and pressure. Okay, I've already done that one, but let's do the one that's actually real interesting. So I'm not using the board. Let's do G. Obviously, G is the last transform that we have. So I'm going to start with U. I always start with the basement. Now remember, this is because H is U plus PV, the thing I screwed up. Okay, so U. Okay, so what should come next? Let's get rid of these dependents on U. So remember, I'm starting with U, and U is S and V dependent. How do I get rid of the V? Minus V times pressure, but the conjugate of V is negative P. So minus PV plus VV, right? See, it's H. Right, H. G is H. What? You already know? Minus, right, okay, so, okay. Let's get rid of the S dependence on U. All right, so what am I going to do? I'm going to subtract S times what? Right, because the conjugate of S is T. Okay, so that's the ultimate Legendre transform. So U has functions of V and S, and now they've both been removed. I can't go further with this, by the way. So all of our energy functions are U, H, A, and G. There are actually further ones, but we can say those for grad students. That's enough for right now. To know that I've done this right, I calculate the change in G. Let me go ahead and just write the whole thing out, because I hope that this is child's play. The change in U is, let's see, I'm going to do TDS. I'm going to do PDV minus PDV because this is the change in U. Here, let me, just in case you have a little bit of trouble in your notes. That's where that's coming from. Right, remember, U is a function of S and V. Okay, now let's let PV change, so that's plus PDV plus VDP. Okay, let's subtract the change in TS. That's minus TDS minus SDT. Yeah, it's kind of a pain. Yeah, but I mean, at the same time, can you subtract, right? I'm pretty sure you can. That's gone, that's gone. Okay, so what I'm left with is VDP minus SDT, which means that therefore G is a function of P and D. Which, by the way, I'm about to prove, this is kind of a biz knocker, by the way, that G, the change in G, a negative change in G tells you whether something is spontaneous, tells you whether total entropy increases in a chemical process at constant P and constant T. Now remember the question of, does the bird fly at constant pressure, constant temperature, adiabatic, isothermal? Does the protein interact with the substrate at constant pressure, constant temperature? Remember all that? Right. You know why? That's right now. Right now is why I set up that question about a month ago. So for you to be thinking about why this one is actually more important than U or H or A. Because the world is a constant pressure, constant temperature world. It's a practical thing. I don't know, if whatever created everything decided to put a metal box around this Earth, then I wouldn't care a flip about G, I'd care a flip about A, because we'd be a constant volume system. But because there's no giant metal box on the Earth for whatever reason, then G is the guy that I really care about. All right, so with that, let me, oh, I left my notes, my office, that's great. I'll do this off the top of my head. We'll see how that goes. Now, I want to do the Clausius inequality to show you that the negative change in G is total entropy increasing at constant pressure and temperature. And when you do A, you're just going to basically repeat what I do. Again, it's on your homework, and it may be on the test. You're going to do that with A, but it's actually going to be easier. So every year I flip this, by the way, which one I do in class, which one I do on the homework for obvious reasons. You're kind of lucky. You get the G. The G is actually a little bit harder. Okay, Clausius inequality. I'm just now blanking out. Okay, now remember, minus T is greater than or equal to 0. Divided by T. Okay, I'm just doing this by memory because I stupidly left my notes. Okay, change in entropy over the change in irreversible heating is greater than or equal to 0 in case of reversible. Okay, multiply by minus T, and now I've got change in heat minus TDS greater than or equal to 0. And now what I want to do is hold P constant. Now remember, when I ask you to do this on a homework or a test, you've got to remember that at some point you've got to start adding stipulations for the actual way the process is done, or you're not going anywhere, right? You've gone as far as you can go. Now start making stipulations. Actually, when I was writing my notes that are sitting on my office, I hope I do this right.
Quality switch when you multiply by minus.
Yes, right. That's right. Thank you. Because I don't have notes, so thanks for catching that. Takes me about an hour of video time. Okay, if I'm holding P constant, that makes the change in H. Okay. Now, this is where this gets kind of tricky. And unfortunately, I'm going to have to do a side derivation. And what I've got to remind myself is G is U plus PB minus TS, which is H minus TS. And therefore, the change in G is the change in H minus TS, and change in H minus TS, that's minus TDS minus SDT. And I did it again, didn't I, right here? Sorry. A little out of it. What's wrong with me? Okay, so hopefully you're okay with that. Now, here's the trick. And I'm going to go back to the derivation. Let me write it down up here, because I'm really using the board like a maniac today. Okay, so here's where I'm at, and I need to want, for my own selfish purposes, I want to see this. I want to see this in here, and I don't. But I could by doing this. See, I'm close. I got dH, I got minus TdS. If I only had minus SDT, I've got G in it. But I can't just subtract something out, can I? Or can I? Okay, so again, I'm working with an equation. I can't unbalance the greater than equal, so I think of it as an equal. You can't just start adding things in and have that equality remain, right? You can't just start changing functions and not change what they mean, right? So, okay, so I've subtracted SDT out. What can I do to negate that? It's really easy. Add it back in. Right? There you go. And now that I've done that, nothing has changed. And that's what I mean by nothing has changed. It's still less than equal to 0. And now I recognize that this is a change in G. Okay, problem. I'm trying to get back to high school where you learned that a negative delta G is spontaneous. I'm halfway there, but I got that problem. Right? You can't say that negative G means spontaneous, not yet. What can I do? Now remember, I just said a second ago, how do you get out of sticking points? No, earlier. How do you make progress on these Clausius inequality?
Set limitations.
What? You what?
Set limitations.
Right. You set limitations. You make stipulations. That's actually what I said. You make stipulations. Constant what? Constant T. No, constant T. Constant T. S is for U. S is for H, not G. At constant T, this term goes away. I'll do that. And dG is less than or equal to 0. Okay, now, and also remember the big picture that everything I've done is with the Clausius inequality. The Clausius inequality tells me about total entropy. Manipulations that I've done, sure, still don't change the fact that I am working with the total entropy. I have technically multiplied it by minus temperature. Now that does actually kind of screw it up a little bit. And that's why instead of G being, say, greater than 0, it's actually less than 0. That's the minus part. Notice also that it has the wrong units. It's joules, it's not joules per K. Because, again, I multiplied the total entropy times minus T. Okay, now if you can just get over that, which you should, in fact, I usually don't even bring that up. I just kind of hope that I can gloss over it. This stipulates that the total entropy change is positive. A process is spontaneous, means that delta G is negative. This is saying that. This is saying the total entropy is increasing, but the manipulations require constant T and constant P. That's why we told you this in high school. That's why we told you this in freshman, because the bird flies, the proteins interact, and the constant temperature, constant pressure world. And it is true that occasionally chemists do things at constant volume. Theoreticians, if any of you actually end up going to grad school and you do computer simulations, which is probably one or two of you actually, you do those at constant volume anyway. People do things at constant volume. It's not very common. No one does anything at constant entropy. That doesn't make sense. So there you go. And now also recall, you might want to put the star by this. You're going to do all of this for A on your homework. It's actually slightly easier. So remember, you got kind of lucky this year. What else do I want to say? What did I do? Oh yeah, I showed you this. And sorry, because I had a broken my notes, I got kind of confused. All right. Well, with that, I want to start showing questions.
So why did you add us to?
What? Huh? You got to help me here. What?
A plus us to. Yeah, that's fine. Yeah.
Well, I added 0. Right, now remember, I'm trying to get to G. Yeah, this is the change in G, and then I had this from the Clausius inequality, so I added and subtracted the same number.
Oh, we added both. Oh, okay.
Right, so I added 0. Remember how in math, when you, especially when you started to get to high, like junior, senior level high school, adding 0 or multiplying by 1, right, Q over Q or something, made all the difference in factoring things. And even though you didn't really do anything, so this is one of those clever cases. I mean, adding 0 is brainless, yet it does something very clever. So it's something I always appreciate is, again, you're doing it on your homework. Okay, with that, let me give you a little kick in the pants about something. Remember how I said that, hopefully you're convinced now, that I always ask new questions on exams because what I'm going to ask, especially the harder questions, are going to be what's the change in x with respect to y at constant z? And how I can always ask new questions because I have a whole bunch of letters. Yeah, remember how I said that there are 48 possibilities to a gas expands, a gas contracts? That's today. I just gave you the last three, A, G, and technically yes. I haven't been doing derivations with S, but I start today. So that's why I want to do a whole bunch of derivations with S, because I can and I will. And I think it is meaningful because, unfortunately, yeah, I can ask anything, and there are multiple ways of doing these questions, and I'm going to show you all of them for the ones I'm going to ask, the ones that I know of. I'm sure there's ones that I don't know about. But it does, the value isn't, I don't want you memorizing this stuff, I just want you to remember some basic rules of algebra, product rules from calculus. That's as far as we're going to go, which is actually not far at all. And if there's value to this, is to remember that everything is interconnected, which is true. So you know that if you change this, then that thing I change will change that, and then that thing will change that, and that thing will change that, and I don't want that. Well, see, you got to think beyond high school level, right, about all the interconnects of things. And if you can follow what I'm doing, you get that. So anyway, I hope that's the value, even if just justified by existence. I don't want all this just to turn into a giant math class with intractable problems that don't mean anything. Regardless, I wanted to just show you a bunch of derivational tricks with entropy. Now, because I do not have an entropy meter like I have a thermometer, and entropy is the most important thing ever, I need to find clever tricks to figure out what the change in S is, or equate a change in S to something else. Anything else is measurable except S, unfortunately. Kind of finding a world truth with us. Okay, so, let's see, actually, what am I getting to? I'm going to do, so here's how I'm going to do this. Here's what I'm going to do. So I'm going to throw something at you. Now again, remember, the world is my oyster because dx, dy at constant z, I can just start throwing in letters as long as it's T, P, V, S, A, G, blah, Q, W. I mean, it just goes on and on, right? So let's throw some up and just start doing them. Now, what I'm looking for, and then of course I will show you how to start these. Anything you start with will get you the answer. It's just a matter of steps. But I'm looking for an equation with a change in S. And let me tell you, I'm also thinking that I need to find a V in it too. And it'll be clear why. But what should I start with if I'm looking for an equation with a change in S and a change in V?
U.
Right, U. U is a function of S and V. Right, now of course I'm going to tell you that so that you don't start with the wrong one and then do 20 steps, which I tell you you should never do 20 steps. And for some of you on the test, there's a handful of you who did 20 steps even on the extra credit, and you should have known that that was not correct because I don't do that. So anyway, I'd asked for this. I told you to start here, and hopefully you know that you just start, you use the rules of A equals C, divide both by D. And let's say I got T ds dt minus P dv dt. And what do I hold constant again? Right, D. Why? Because that's what I asked. Right, there's no magic to that. Remember that you can hold anything you want constant. Now, when I do this stuff, when I ask this, I know that I'm often looking for this and this. It doesn't have to be true. This stuff is unfortunately complex. There's no easy rules to how to... There's some general things that I tend to look for to find the simplest route. And it tends to be find this and this, which means write an equation that has this and changing this in it, which is U. It tends to be the quickest one. Why? Anything I can get rid of? Anything I can get rid of? V, right, 0. Now you see that? Because I was going to hold V constant, I wanted to find it changing the equation because I knew that no matter how complex I'm trying to solve, I'm going to eliminate a term. Again, ultimately, don't worry about it. I'll make sure that you start out in the right direction. But anyway, you see the strategy, right? Okay, you seen this one before?
Yeah, let's see.
Yeah, CV. So let's just do it. CV over T is ds dt, constant V. There you go. That's the answer. So last question on the second test, you've answered it. Except that's part A. Let me give you part B. Right? And I will do this. Now, part B says, to integrate, what part B says, if ds dt is constant V, is CV over T, and of course I did that to give you the answer to part A. You know I do that kind of stuff. What I'm asking for is then, what is the macroscopic, but you integrate it. Just integrate it and tell me is it correct. Okay. Now again, A over B is equal to C. So A is equal to B times C. And therefore I integrate both sides and I get delta S is CV ln TF over TI. Right. And, for some of you, by the way, on the unit section, some of you did not take derivatives, you integrated. Don't do that. Come on, that's first month of calc. Hopefully you had that in high school. Okay, we're familiar? Right, now I should have an N in the CV per mole, right, maybe? But what happened to the volume part? Why did now, if I did this right, why didn't the volume, remember this is half delta S. There's an NR ln VF over VI. Why did it not come out? It should be there. Why not? Right. I started this with a constant volume. There was no work. And it turns out that ln VF over VI comes about from doing work on the system. That's the entropy change from doing work. But if I held the volume constant, there should have been no work. There should have been no entropy change from changing volume if volume never changed, right? So I was only left with the temperature component. And it's exactly what we did before. It's just a new way to derive it. And it's also a way you can know about it. Okay, so why don't I, let's see, what am I doing now? Okay, why don't we do that? Let's do the SD, let's do a different one. Again, let's just do a whole bunch of practice, and then in the next hour, a bunch more practice. Let's do this. And this example, let's see, what am I doing? Okay, so now this is an example of why my little handy-dandy rule isn't necessarily perfect. What I'm going to do with this one, I'm actually going to start with the change in U, just because I know that actually this one's kind of easy. I'm going to do a change in U, so that's PDS minus PDV, and let's divide by D. You see now again, because I'm looking for the change in S, I'm looking for a function that has S changing, and so that's why I'm thinking of U. Now remember, I cannot have a function where S is changing and T is changing. That doesn't exist because they're conjugates. That's why you may be thinking like, well hold on, I'm looking for the, remember I just said that there are some rules about how to figure out what are good starting places, but they're just rules of thumb, they're not perfect. In this case, S and D was what I was looking for because there are functions with S and D changing. In this case, it's like I'm looking for one with S and T changing. There are none. They're conjugates. They can't both change. All right, so that's why I happen to know that I wanted to go with U in this case. And you can see that the reason is that I can't find a 0, but I can find a 1, right. So that, again, it did simplify it. And that's not all. Now let's hold something constant. What else? What else? I got something else going. Right. I can make that 0. So what I've got now is P over T is ds dt. Now clearly what I want to do is be able to rederive my natural log deals with volume. So I did the change in S as CV ln TF over TI. Now I want to do is get that other bit, right? That's actually kind of the reason I'm specifically asking this. And so let's do that. So change in S. So remember that's part A. Part B said if ds is P over T, dv at constant T. Okay, the question is if this is true, so I've given you the answer. What's the absolute change in S? So you do this, P over T dV, you integrate, and you get delta S is P delta V, P over T, is that right? Hold on, is that right? It doesn't look right. I thought I was supposed to get NR ln dF over VI. So I didn't do anything wrong. This, right, P and T are hiding V inside of it. Remember, you can't let that happen. If you bring this out, effectively I've brought these out of the equation as though they are constant. They are not constant. How can I change volume and not change pressure if the temperature is held constant, right? That's impossible. So when I brought that out, I've got a wacky equation, but I've also described something that can never happen. So no wonder I got the wrong answer. So let's integrate it correctly. P over T is NR over V. V, which is of course NR ln dF over VI. There you go. Alrighty, folks. A's on this side.